All right, we're starting a new section. In our textbook, it is 8-6, the radical expressions and rational exponents. And it's really important that before we start this, we do a quick review of our exponential properties. This is a great time to grab a note card or a notebook where you keep notes and jot down your rules. In my classes, I'm not worried about the title of the rule. I'm worried that if you see a to the 0, that you know the rule that it is 1. Anything to the power of 0 is 1. Our negative exponent rule is a to the negative n. Anytime I have a negative exponent, you're going to take the reciprocal. If that negative exponent is in the denominator, it's going to come back to the top. Remember, it's only what's on the variable. So if there's a number in front, the negative exponent only affects what it's on, as in the variable, or what is in parentheses. All right, product of like bases. Whenever I'm multiplying like bases, I keep the base and I add the powers. And whenever I am dividing, I keep the base and I subtract the powers. Okay, so we have some examples there. We have some other review rules. When we have a power to power, we multiply. When we have a product to a power, we have a times b to the power of m. And that would be a to the m, b to the m. So it's almost like distributing that power. I can do that with multiplication, and I can also do that with division. Everything gets the power. So I can only distribute the power in multiplication and division. I cannot do that over addition and subtraction. And then there's one rule that we have talked about but not really focused on. You can see that these rules came from mathaids.com. The rational exponent rule. And so anytime you have a rational exponent, as in a fraction, that's what we're focusing on. Not just a power of 2, but an actual fraction here. The numerator stays as a power on your base, but the denominator becomes the root. So this would be the y root of a to the x. And if I have something like 2 to the 2/3, this becomes the cube root of 2 squared, or the cube root of 4. So this is a rule that we have alluded to. I've talked about a square root being the same as a power of 1/2, and a cube root being the same as a power of 1/3. And this is where we're going to use that. So again, I'll just quickly show these here. So here are 2 of the rules, 2 more. And the last 2. So these rules are going to be used. It's really important that we use them properly. All right, so we're going to go ahead and jump into our notes. And we are doing part 1, and then there will be another lesson on part 2. All right, so you're familiar with finding square roots and squares of numbers. Square and square roots are inverses. We know that from solving quadratics. We also want to remember that the square root corresponds to larger powers. Okay, or sorry, there are roots that correspond to larger powers. So we can be talking about higher roots, something more than a square root. Now, a couple things. 5 and -5 are both square roots of 25. Remember, 5 times 5 is 25, but also negative times a negative gives us that same positive. So anytime I have a square root of a number, I would be solving it. I would be getting 2 answers, the positive and the negative. All right, if I have a cube root, 2 is the cube root of 8 because 2 to the 3rd is 8. I only have one answer. The cube root of 8 is just 2 because I can take the cube root of a negative. Okay, and we're going to talk about that. 2 and -2 are 4th roots of 16. So you have to think about this. It grows really fast. 2 to the 4th is 16 and -2 to the 4th is 16. So anytime you have an even power like a square root or a 4th root, you can have 2 outcomes, a 2 or a -2, a 5 or a -5, because I have 4 of these. So I'd have 4 negative signs, and every 2 cancel out. That's why I have a positive. And we have in general, a is the nth root of b. Okay, so this is a little confusing, right? A is the nth root of b if a to the n equals b. Okay, so my power is the same idea as I can reverse it and take that root of b. All right, so let's go ahead and put some information down to help us. The nth root of a real number, a, can be written as a radical expression, nth root of a. All right, and that number goes in the crook of your radical symbol, where n is called the index. All right, or plural would be indices or indices, depending how you say it. All right, so the index of the radical, and a is called the radicand. So a is the radicand. It's the nth root, and n is the index, and that's your radical symbol. When a number has more than one real root, the radical sign indicates only the principal or the positive root. So when I go to put the square root of 4 in my calculator is only going to tell me the positive root or the main principal root. But I know that I have 2 roots. Okay, so we have some rules here. If I have an odd index or an odd root, okay, I'm going to have 1 real root. 1 real root. All right, so an example, the cube root of 8 is 2, and that is the only outcome. All right, why is that true? Because 2 to the third is 8. And just on a side note, if I would take the cube root of -8, I would get -2. And that's what's different. I cannot take the square root or the 4th root of a negative number, but I can take the cube root of a negative number, because that would be -2 to the third, which is 3 negative signs. And so I have that 1 negative sign left over to get me that -8. So that is why I only get 1 real root, because if I'm taking the cube root of a positive, I get a positive root. If I'm taking the cube root of a negative, I will have a negative root. All right, if I have an even index, meaning an even root, and I have a positive radicand, remember the radicand is the number underneath the root, okay, then I will get 2 real roots. 2 real roots. So an example would be well, we already had that on the top, but the 4th root of 16, that's what it looks like. The 4th root of 16 is either a positive 2 or a negative 2. And that is because -2 to the 4th is a positive 16. You have 4 negative signs. And 2 to the 4th is also 16. All right, if I have an even index, which again is an even root, but I have a negative radicand, so the number under the root, then I have no real solutions or no real roots. However, I could have some imaginary ones if we're talking about square roots. All right, so I have no real roots. So the 4th root of -16 is not a real root. There is no number times itself 4 times it's going to give me a negative, because the negative signs would always cancel out. So I can't take the square root of a negative without imaginary numbers. I can't take any even roots, because I'll have an even number of negative signs. All right, the radicand of 0, or the root of 0, and it doesn't matter what root I take of 0, will always give me 1 real root. And that 1 real root will be 0. So whether I take the cube root of 0, I will get 0. If I take the square root of 0, I will get 0. And I just want to stop and remind you, we have up here the nth root of the square root of a. N is your index. And so if the index is not 2, we have to show it. So you can see that this is a square root here. And there really is a 2 there, but it's used so commonly that we don't put it there. It's almost like log base 10. We just write it as log because it's the common log. That any other index has to be shown, okay? So let's go over some examples here that are pretty much laid out for us, and we'll keep our rules right here. There we go. So it says find all the real roots. So we're only focusing on the real roots here. So the 4th roots of 81, I would write it like this, the 4th root of 81. Make sure it's not, the 4 is not out front so it doesn't look like multiplication, okay? A positive number has 2 real 4th roots, because positive 3 to the 4th and negative 3 to the 4th are both 81. Now, how did I get that if I wasn't sure? Now, some of us have different calculators, but on this calculator, trying to get a good angle here, on this calculator, I'm going to type in the 4, and then I'm hitting my second function, and then my any power key, there's my any root key, the x root. So in my calculator, I'm telling you that it's the 4th root of 81. So this x root has to be there, and it's defining it. Some calculators pop the 4 up in there. Some calculators, graphing ones, you have to go to the math key, and then you can find that x root key. And then there's some of the calculators that don't have the readout, that you type in the 81, then the root sign, and then you define it where it's backwards. Now remember, this is only going to give me the principal root of 3. I have to remember that it's an even root, so I'll have two outcomes, 3 to the 4th or negative 3 to the 4th. So look, 3 to the 4th is 81. Now, if I put it in parentheses, which is what I need to do, and I put the power on the outside, I will get a positive 81, because it just took negative 3 times negative 3 times negative 3 times negative 3. Well, that's 9 times 9, it's 81. If I mistype it and I do this, I will get a negative 81, because the power was only on the 3. The calculator did not put the power on that. So be really careful. The other mistake I get, I'll have students tell me, but I use parentheses, and they do this. Well, that was really wrong. Let me try that again. Negative 3, and then they do a power of 4. There. This is a problem because, again, the 4 is only on the 3. The parentheses are not around the 3. It's just around the whole thing. So be really careful. We don't want to enter it that way. The proper way to enter this is in parentheses, and we get that 81. Okay, enough of that. So if 3 to the 4th is 81 and negative 3 to the 4th is 81, then the roots are negative 3 and positive 3. So we'll get two roots. All right, the cube roots of negative 125. A negative number has one real root. So the first thing is, when we see this, a lot of times we think, well, we can't take a root. I can, because it is the cube root. And the cube root means what times itself 3 times. 1, 2, 3. And so a negative 5 times negative 5 times negative 5 will give me negative 125. The first two negative signs cancel out, and then I'm left with 1 there. So negative 5 to the 3rd will give me negative 125. If I try to take 5 to the 3rd, I will get a positive 125. So there is only one outcome when you have an odd index. So it has to be negative 5 to the 3rd, and that will give me my negative 125. So the root, again, is negative 5. All right, the 6 roots of negative 729. Well, the 6th root would be an even index. I cannot take an even index to take a root of a negative number, because that would mean I'd have 6 negative signs or no negative signs, and I need a negative 729, so that cannot happen. So a negative number has 0 real 6 roots. Anytime that you have an even root, you cannot take that of a negative number. All right, we'll keep going here. We have some more examples. So let's find the 4th root of negative 256. These are good examples to pause, try on your own, and then come back. I'm going to rewrite this as the 4th root of negative 256. Okay, so if I'm not thinking about it and I put it in my calculator, put this under here, and I type in the 4th root of, make sure it's the x root, not the square root, negative 256. Yeah, I get a domain error because the domain is your input and I can't put that in. Now, if it was not a negative number, there is a 4th root of 256. It's 4. 4 to the 4th is 256. Negative 4 to the 4th is 256. But there is nothing times itself 4 times that will give me this. So there are no real roots. And again, notice the directions are asking for the real roots. We're not worried about anything imaginary. All right, what is the 6th root of 1? So the 6th root of 1. Well, a lot of people just want to say it's 1 and they want to move on. But isn't it a positive 1 or a negative 1? That is my answer. All right, why is that? Because 1 to the 6 is 1, but negative 1 to the 6 is also positive 1. All right, the cube root of 125. Well, we can type that in our calculator. Maybe we know it. 5 times 5 is 25, times 5 is 125, and I get 1 real root. Because if I take negative 5 to the 3rd, I would get a negative 125. Okay, so I'm reminding you that all of these properties that we're going to use next are properties that we have learned back in lesson 1-3 at the very beginning of the year, and that have come up a lot throughout the year. Now we're going to add on to those properties the product of nth roots. And so a and b both have to be greater than 0. Okay, so Make sure you have your bases greater than 0. So let's go ahead and talk about these roots and how they affect us, and this is what is new for us today. Alright, so I'm going to give you an example, and we are going to take the cube root of 16. Okay, well, there's not a nice cube root of 16. So we had spent some time in class going over cubics, sum and difference of cubes. So we should be familiar with our cubic numbers, and 16 is not one of them. If I try to take the cube root of 16, you'll see that I get a decimal. Now there are some calculators out there that give the exact answer. If not, we're going to have to break it down, and it's really good and important to have that skill. So what am I doing here? Well, just like before, when we found the biggest perfect square that went into a number, we're going to find the biggest cubic number. So it is really useful to have a list of cubic numbers. And so maybe that's something you do off to the side on a note card. But cubic numbers, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 4 cubed is 64, 5 to the third is 125, 6 to the third, I'm going to double check myself, yeah, 6 to the third is 216, 7 to the third is 343, 8 to the third is 512, and I think we could stop there. We'll do 9 to the third. And we get 729, and then we should know that 10 to the third is 1,000. So these are your cubic numbers. So we are looking to focus on any of these. So when I have a number like this, and I have the cube root of 16, I'm going to look and say, well, 8 does go into 16. Nothing else goes into 16. And 8 is a cubic number. So I'm going to do what we did before, and I'm going to break this down. So instead of writing it as 16, I'm going to write it as 8 times 2. And the 8's what I'm focusing on. And that property that we're going to talk about allows me to break this down to be the cube root of 8 times the cube root of 2. And notice every time I write my cube root symbol, I have to have the index there. The cube root of 8 is 2, so I have a nice whole 2 out front, and then I have the leftover root. And so we're going back to simplifying roots. Okay, the algebra, this is the rule. The nth root of a times b is equal to the nth root of a times the nth root of b. So this is not a new rule. This is a rule that we had with square roots. We had the square root of a times b is equal to the square root of a times the square root of b. This is telling you now that you can do it with any index. All right? And again, your goal is to find the biggest perfect cubic number, the biggest perfect square, the biggest power of 4. And you're going to see a lot of these numbers are going to repeat. We try to keep a small range of numbers. All right, now we're going to do the flip side of that. We're going to do the quotient. So if I give you an example, and we're just going to do the square root of 25 over 16, I can just look at that and know that I get 5/4, but what am I really doing? I'm breaking it up and giving the numerator its own root and the denominator its own root. So I can only do this if it's the square root of a fraction, then the top and bottom get it. If the 16 was not underneath the root, I can't do that. The square root of 25 is 5, and the square root of 16 is 4. And right now, I'm only talking about the principal root. We're just focusing on what it is when we break it down. We're not focusing on how many real roots we have, just the principal root. Okay, so this rule is the nth root of a over b is equal to the nth root of a divided by the nth root of b. All right, so again, same rules we've used. Now, we are stepping up our game from what we did. So not only are we dealing with higher index or indices, we are dealing with variables with higher powers. All right, and that's fine, we can do that. So what I want to do is it says factor into perfect cubes. Well, luckily, 27 is on my list of cubic numbers. So this would be the cube root of 27, and then the cube root of x to the 6. So I broke that down. But I want to think about this. Go back to your power properties. Couldn't I rewrite that x to the 6 as two groups of 3? So why do I want to do that? Well, a power of 3 and a root of 3 are inverses. So if I break this up, remember when I multiply bases, I add the powers. So I rewrote this as x3, x3. So the cube root of 27 is 3, and then the cube root and the cube cancel out, and the cube root and the cube cancel out. So I'm left with 3x squared. There's other ways you can look at this. We talked about this rule that is going to be our focus in our next lesson. We did talk about this rule. I had the cube root of x to the 6. I could write it as a fractional exponent. So if I rewrote this cube root of x to the 6 as x to the 6/3, you can see that I get x squared that way just by following the rule and reducing my fraction. And that is my final answer. Okay, now we have a division problem. And the first thing I'm going to do is I see this, and I'm going to break it down. I'm going to have the cube root of x to the 3rd over the cube root of 7. Okay, well the top is easy. The cube root and the cube are inverses, they cancel out. The bottom is an issue. And we have to rationalize the denominator, okay? You cannot leave an irrational number down here. So since 7 wasn't a cubic number, I can't take the cube root of it, I have to deal with that. So I want to remind you that when we had a square root that we had to rationalize, we would square it. We'd multiply it by itself. Well, to get rid of a cube root, I have to multiply it by itself a total of 3 times. So I really need to take this times the cube root of the cube root of 7 squared. Now maybe I write it out 3 times. Here's 1 cube root of 7 times the cube root of 7 times the cube root of 7. All right, so what am I doing? Well, isn't there 1 here? And now there's 2 here. So if you think about this, my new denominator is the cube root of 7 all to the power of 3. Because when I multiply that cube root of 7 times the cube root of 7, I add the powers. So we are using those power properties. And so why did I do that? Well, if I just multiplied it by the cube root of 7, I'd have the cube root of 49, or the cube root of 7 squared. And there's nothing I can do with that. But if I have the cube root of 7 to the 3rd, or the cube root of 343, that cancels out and leaves me a denominator of just 7. The problem is I didn't balance it. Whenever I change the bottom, I have to change the top. So that would be the cube root of 7 squared. Okay, now this is where it gets a little awkward for some people, but you have to trust the process. The x is going to stay the same, but it's not proper to have a cube root and a power sitting here. So I definitely cannot take the cube root of 7. And the order of the operations here, whether I take the cube root first or I do the power first, does not matter. They're equal playing fields in the order of operations world. So I'm going to go ahead, even though this is outside the parentheses, I'm going to take 7 and square it. So I'm going to still keep my cube root, and 7 squared is 49. And that's what I'm going to do. I cannot take the cube root of 7, so I'm going to simplify it with the power. And then I'm going to look at that cube root of 49. Can I break that down? Okay, well, 49 is not divisible by 8. It's definitely not divisible by 27, and 64 is too big. So there are no cubic numbers that divide into 49. So my final answer is just an x with the cube root of 49 all over 7. And remember, you cannot reduce the 49 and the 7 because that is a cube root. And so that 49 does not reduce with the unlike term there. Okay, so this is something that we need to practice. Dealing with rationalizing a denominator, remembering that, and then taking it one step further, plus all of our power properties. Okay, well, here are some check it out problems. These are really our last 3 examples, but I think this is something that needs a lot of attention and a lot of practice. So good time to pause and give it a try. All right, so when we're going to break this down, I'm going to break it down to the 4th root of 16, and boy, do we luck out here. It is the 4th root of x to the 4th. Okay, so maybe I don't know what the 4th root of 16 is, so I take my calculator and I take the 4th root by defining it of 16, and I get 2. Okay, so the 4th root of 16 is 2. So that simplifies, and the root and the power cancel and leave me just a 2x. Now, there is more to go with this, and it's something we can focus on later. When we do problems like this and we have variables, there are domain restrictions. And so There are things that we do have to talk about eventually, but right now we're focusing on this. Okay, next problem, we have division. So I'm going to break it up as the fourth root of x to the 8th over the fourth root of 3. Okay, the fourth root of x to the 8, you can do a couple things with. You can break it down to two groups of 4. I'm going to break it down and think about it as x to the 8/4, which is really just x squared. All right, here is the issue. I have the fourth root of 3, and there is nothing I can do with that. The fourth root of 3 is a really, nasty, irrational number. So I have to rationalize it. So if I have a fourth root, the power that cancels a fourth root is a power of 4. So I have to take this times something to the power to get it all the power of 4. So I'm going to multiply it by itself, but I have to do it 4 times. So imagine me writing this out. Here's 1, write it out 2, 3, and 4. So I already have one of them. I need 3 more. That's what you want to think about. I already have one of them here. I need 3 more. And then that builds me that power that I have, the fourth root of 3 to the 4th. And so that's going to cancel and leave me just a denominator of 3. Okay, so the denominator does not cancel out completely. We're canceling out the root. Now, whatever I do to the bottom, I have to do to the top. Same thing, same power. There is no fourth root of 3, that's why we're in this situation. So I'm going to go ahead and take 3 to the 3rd, and I would double check myself on the calculator, but 3 to the 3rd is 27. So I have x squared times the fourth root of 27. Now, before I say I'm done, I want to check and see if there are any powers of 4 that are in 27. So we would say powers of 4. I think that's the best way to write it. So 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, and I'm already above that, but just to give you an idea, what was I on? 3 to the 4th, 4 to the 4th is 256, and 5 to the 4th is 625. So again, this is 1 to the 3rd, this is 1 to the 4th, and so we can see that 27 doesn't divide by 1, well, 1's not going to help us, doesn't divide by 16. So this is not going to break down, but there are times that breaks down. So my final answer is x squared and then the fourth root of 27. It's proper, whatever is broken down or outside the root should be out front, so it's not ambiguous, so we know it's not part of the root, and then watch your power and watch your root that they go in the right spots. Okay, we have one more here, and it's a little bit messy. So you have two options. I could work on breaking down the 7, and then I'm stuck with this. But you see how I have the same base? So I'm going to use my rule that it's really the cube root of x to the 7th times x to the 2nd. Okay, I don't have to write that. I could jump right to the fact that it's the cube root of x to the 9th. So if you think about your property, this would be x to the 9/3, which is simply x to the 3rd. The other way you can think about it is breaking it down, the cube root of x to the 3rd, cube root of x to the 3rd, and so mentally, that's what we're doing. And so the cube root and the 3's cancel, and that's why I'm left with 3 x's here multiplied together to get me x to the 3rd. Okay, so definitely a little bit more abstract, and again, using a lot of prior knowledge. So keep practicing, and I will see you for the second half.